Hello, my name is Lieven Penninck, and I would like to thank the organizers for this opportunity to present the work of my colleagues Michael and Bavo and myself on accelerating meta-atom design using optimization, inverse design, and AI methods. This is an application-focused benchmark. First, a little bit about us. So we are PlanOpSim. PlanOpSim is a company from Belgium that focuses on delivering R&D tools, that means software and design services, to engineers and scientists that allow you to use metasurfaces and flat optics in the most user-friendly way possible. We are happy to have received some support from the Belgian government, IMEC, as well as the EU's Horizon Europe program. And if we look at meta-surface design today, there are a couple of common bottlenecks that reappear in many projects. The first of all, and the focus for today's presentation, is the optimization of nanostructures using full-wave solutions, because the structures, as you well know, are sub-wavelength in scale. We need a full solution to Maxwell's equations using FDTD, finite element method, or RCWA, or any other method to know their behavior. All of these algorithms, no matter which one you choose, scale pretty poorly with increasing degrees of freedom. That means that calculation times can take very long, going to several hours to several days, and that they are also memory intensive. And that leads to the next bottleneck, that is, it is difficult to optimize metasurfaces over large areas because of these memory limitations. This can be circumvented to some extent using multi-scale methods, as we do also in our software, but those then inherently require some form of approximation. Going then even from components to systems, combining metasurfaces with other metasurfaces or with classical optical components, a link to ray tracing system is needed, which is at the moment underdeveloped. The models that do exist ignore higher order diffraction and often also the amplitude and discretization effects of the meta-atoms themselves. To show that this is a real problem, if we look at an estimate that I got from the Lumerical website, they calculate there that for a large-scale project, calculation costs can run up to $11,000 per month. So there is a real need to speed up the calculation process if we want to make practical sized metasurfaces. In optimizing metasurfaces, there's a general framework that's used throughout, is that we start from an initial solution, which then propagates through an optimization loop with different calls to the full wave solver and an optimization algorithm suggesting a next candidate solution. This typically goes on through 10,000s of these different structures, be they either parametrized structures or arbitrary shaped structures. And the time this takes is basically determined on the one hand by the number of solver calls we need to make and how long each call takes. So if we want to speed this up, we have two options. Either we pick a very clever optimization algorithm so that we only need few calls to reach the solution, or we make each loop run very fast using a fast solver, and that will be the second part of this presentation. The good news is that these approaches are, so to speak, orthogonal, is that in the sense that they can be combined with each other for even additional speed increases. So that's the topic of this presentation. How much can we speed up and how? And I hope to get that with the first part on optimization structures.